This is Geometry Lesson 2.1, the need for definitions. The big idea says that definitions of mathematical terms are explicitly stated both for clarity and because it's important in communication that people use the same meaning for a term. So we're going to be talking about definitions, what makes a good definition, what makes a poor definition, and why are they important. So as I look at these shapes, the first question says, is this a rectangle? When I look at this first one, I would say yes. It appears to be a rectangle. But if then I said, well, can you prove it? I might change my mind. Okay, this appears to be a rectangle. It looks like it has the characteristics that a rectangle has to have. But if you look at this one is a rectangle. It doesn't just appear to be a rectangle, it is a rectangle. So what's the difference between the two? Well, this one has these little markings. So first of all, let's make sure we understand what those markings represent. Those markings show that those angles are 90 degrees or right angles. So in order for me to say that this is a rectangle, I must see that there are right angles. So while this one appears to be a rectangle, I can't prove that it is unless I have these right angles. So what's the definition of a rectangle? We'll actually write that here in a minute. But good definitions are needed in geometry because they form the basic building blocks along with our assumptions or our postulates to prove theorems. And so we're going to talk a lot about proving these different theorems. In order to do so, we're going to have to fall back on these good definitions and assumptions. All right, so before we actually define what a rectangle is, let's talk about why these attempts at defining a rectangle are not so useful. So number one, a rectangle is a figure with a right angle. Why is that not a useful definition? Not. Well, because I can draw another shape that clearly is not a rectangle that has a right angle. So I've just given a great counterexample to show why this is not useful. Just saying that a figure has a right angle is not enough to call it a rectangle. A rectangle has corners. Well, I can draw a shape that has lots of corners. It's kind of an ugly looking shape, but it has corners. That's not a rectangle, so this is not a useful definition. A rectangle is a four-sided shape. 1, 2, 3, 4. That's a four-sided shape. Again, not the prettiest looking shape, but that's not a rectangle. Okay, so that is not a useful definition. So if we go back up here now, what is the definition of a rectangle? It is a four-sided shape. Now that's not enough. We just said that down here. But a rectangle does have to have four sides. It's a four-sided shape with, and this is where we fall back here. We know this is a rectangle because it has four 90-degree angles or four right angles. So that's a good definition. That defines what a rectangle is very specifically and clarifies what is a rectangle and what just appears to be a rectangle. All right, so if we flip this over, we're going to take a look at these six figures that are drawn below. All of them share some characteristics. They all have straight sides. We're not looking at curves. And they all enclose a region, meaning they're not open. It's not some straight sides that don't connect. They are enclosing a region. There's something inside that's enclosed. There's no opening. That's another way to say it. And these are all characteristics of polygons. Okay, and these are all polygons. But if I just gave you these pictures and said, there it is, that's what a polygon is, you don't really know the definition just by looking at those. So just because they share some characteristics, that doesn't define them. This doesn't tell us exactly what a polygon is. Now, we're not going to go into the actual definition of a polygon. That's coming up in a couple lessons, but we are going to look at two different types of polygons. So the basics that we need to know right now is a polygon has straight sides and encloses a region. We'll get more specific, like I said, in the coming lessons. But we are going to classify these polygons as either convex or non-convex. Now, before I even started looking at what this specific textbook defined a convex set as, I already knew what convex was. And when I read this definition, I almost felt like I didn't know what it was anymore because it was so confusing. Let's go ahead and read it. A convex set says a set of points in which every segment that connects points lies entirely in the figure. If you read that 4 or 5 times, I still don't think you're going to understand what that means. A set of points in which every segment that connects points lies entirely in the figure. So it took me a while to break that down and try and figure it out. And I already knew what convex was. I could identify a convex shape and a non-convex shape. And this definition was still confusing to me. So I came up with this non-convex set definition, which I think helps us understand what this means. So a non-convex set is dented. We'll look at that. And it has segments that connect points that lie outside the figure. And that still maybe sounds a little confusing. So it has segments that connect points. So all of these shapes have points. The corners are points. A non-convex set has segments that can connect points and they're outside the figure. So if I look at this shape right here, there's 4 points. And if I connect any of them with a segment, all of those segments are inside the shape. The edge counts. None of these segments, even if I go from this one to this one to this one, any points that I connect are inside the shape. Well, a non-convex says it lies outside the figure. Therefore, this is the opposite. This is convex. It's a set of points. So here's your 4 points, a set of points. Every segment that connects those points lies entirely in the figure. Connecting points with a segment, and the segment is inside the figure. So let's look at the opposite of that. A non-convex set. This would be non-convex. Now let's take this point right here. If I connect it to this point, or this point, or this point, it's inside the shape. So I have not proven why this is non-convex yet. But if you take a look at this point right here, and this point right here, if I connect them with a segment, I'm going to draw a dotted line for now. A segment is solid though. If I connect them with a segment, that segment is not enclosed inside the figure. The figure covers all of this area, and that line connecting 2 of the points lies outside the figure. And this is non-convex. So these are good definitions. They are very clear while they're wordy and confusing. Once you kind of break them down, they are very clear about the difference between a convex shape and a non-convex shape. So let's slide down here and try a couple out. We're going to label each as convex or non-convex. So this one, if I take a look at this point and connect it to any of the other points, I'm inside the shape. I'm inside the shape, inside the shape. This would be considered convex. How about this one? Well, some of these points maybe, but this one, if I was connecting this point and this point, I would have to go outside the shape. And clearly, if I connected those 2 points, I am outside the shape. This is non-convex. And so let's go back to the definition there for a second. We said dented, and this is what we're talking about. There's some kind of what we would consider to be a dent in the outside of the shape that creates this opportunity for points to be connected and not be inside the shape. So if you notice, all of these angles kind of go out on a convex shape, and then all of a sudden we get this dent coming in non-convex. If you look at this one very clearly, this point and this point, you connect them, you're outside the shape. That is non-convex. This one, if I connect these points, they all stay inside the shape. That is convex. This one is pretty much a repeat of that shape right there. So non-convex. What about this one? Well, that connects, and the only other point is here. And no matter where I go, if I take any of these points and connect them with a segment, that segment is inside the shape. This is convex. So let's take it one step further. Can you draw the shapes yourself? So let's draw a 5-sided convex figure. So we don't want to create any dents. And so if we're going to do this, 1, 2, 3, 4, 5. Now my strategy there, this is good. You connect any of these, you're inside the shape. My strategy was to make nice, big angles. Nice big angles every time I connected any of these sides. If you look at these, you got a big angle, and then we create these angles that go inside if it's going to be non-convex. So when I draw a 5-sided non-convex figure, I'm going to draw a couple sides here. 1, 2, and now I want to create, I'm going to go one more. 4, so far so good. 1, 2, 3, 4, and 5. Here's my smaller angle and smaller angle. And now I've got 2 points here that if I connect them with a segment, it lies outside of the figure. That is non-convex.